So the source code contains 4 files. There are 4 files. 2 files are zip file, and the other 2 files are the IPYNB file. So the zip file are the code from the chapters of the book. So if you see this chapter 09, you can upcheck full key. So there will be a lot of code. You can see this is the author code about priority queue, and then sorted priority queue, unsorted priority queue, heap priority queue, and then double link based adaptable heap priority queue. And if you open the chapter 14, I open this one. So in this section, we have like the BFS, DFS, exception, graph, and etc. Okay. So yeah, you have a chapter here, chapter 9 and chapter 14. And let's see the shortest path. The author tried to connect all the contents from the book with the graph. So here, for example, it connects the chapter 9, the heap priority queue, and he's going to connect this into the graph to find the shortest path. Let me check this one. Okay. No module name. Yes, wait a moment. Chapter 9. Okay. So we can put like this one, 0. Maybe it's better to put all the code. If you can see here, the chapter 9, there is another folder, chapter 9. So it will be good if you just put all the code outside. Put here. Okay. And then I have another chapter 14. So chapter 14 and chapter 14. So it means double folder. So it's better for you to put those outside. So here, I will put here. So there will be only chapter 14, okay? Because I put the folder here. It is the folder notebook, and then I have the CH, which is the chapter 09. I have CH14, which is the chapter 14, and the shortest path file is here. Now let me check again. Okay, now it's working. Okay, if you move your files because it is not in the correct folder, then it is error. So if you put all of them in the correct folder, then there will be no error. The author used the priority queue that they developed, the heap priority queue, adaptable heap priority queue, and the partition and the graph. And if you learn from the previous part, we have the graph from the adjacency list. Oh, graph from, I forgot it last time. We have this graph. This is also from the edge list. Okay. So let me repeat again from the graph. So I do not have this graph. This is the class graph, but I do not want to explain more. So you can just use the graph. This is the class graph that you can just import from the chapter graph. And I'm going to make the edge list. This is the same with what we learned before. And from the chapter 14. So last time we have this example. We create the tuple. This is the undirected graph from one airport to another airport with the mileage information. And then I can make the graph. I can make the graph based on the function. This is the information about the airport. So in the chapter 14, we also have the shortest path. Okay, there is the code about the shortest path here. And we need to append this one in order to fit with the code. So whenever we want to check the code, yeah, it goes to this folder. So we are going to use the shortest path. The first is the shortest path tree. So you can make the shortest path tree, and then we can make also the shortest path length. And the shortest path tree will be in the we can make the short as SPT, and the shortest path length we can make as short as SPL. If you want to check this shortest path, so this is the code. There are two: the shortest path length and the shortest path tree. When we are creating the shortest path tree, this is the extra that we learned on the PowerPoint. And then this is the shortest path length. It contains the priority queue. Oh, okay, I copy again here. Yeah, if you want to use from this code, that's also fine. Or if, yeah, I copy this one here to make it easier for you. So let's say I'm going to check the graph 2, and I want to start from LAX. The graph 2, the graph 2 is the graph from the figure 14. This is the data. And then I want to start from the LAX, which is the one of the airport in the information. So here, yeah, is the distance. So the width will be the 1464 from the DFW to SFO, and this is the distance from DFW to LAX, and so on. So those are the information about the distance. If you want to see the SPL with the other way, so I already have the graph. I'm just using the SPL, and then I'm using the graph tool that I already defined in the function, and I'm going to start from LAX. So the information also shown like this one. And if you want to check for every of the element, it's just infinite. So you can check for every of this one. I will open it. Object has no attribute items. Rest is the item here. What is it? So it is all infinite. We need to check for every v. Everything is infinite. Rest items. So this is the rest. So the rest will be this one. So the rest will be in this object. Okay, so we have this first object and the result is infinite. After we have the infinite, okay, we have the LAX and the width is 1464. So it is the same with this one. Okay, that means the LAX, if we go to the DFW, and then there will be another width from the DFW to SFO. This is the width. Let me check again. Why it doesn't work with this SPL? This is the dictionary key. The dictionary key is the vertex object. This is the vertex object. And then we have infinite. So it means this is the vertex object. This is the value. So if I print the K, so it means this is from the LAX to the FW, it is infinite. How can I show this number? So actually this is the LAX to DFW, it is 1464. And then from the LAX to BOS, it is 1235. Okay. And so on. What how to change this infinite? So the SPL print this one. The SPL will print the information on the cloud. So it should be only the K, and then the V is infinite. Yeah, if we see the K, then this information 1, 2, 3, 4, 5, 6, 7 should be this one. Let me figure out later. Wait, let's say we want to send another starting point. So the starting point is from the DFW. Yeah, we have this short path. Okay, this is the shortest path from one node to another node. Okay, the SPL here does not show the content, but the shortest path length here can show the length. Okay, I put this weight, okay, because in this code, I put the print, so we can see the weight. Okay. But in the original, yeah, it shows the weight, but because we just call, they don't print the weight properly. Yeah, last time I also get this problem, so that's why I prefer to use this one. So I put the shortest path length here, so every weight will be shown here. So you can see all the weight. If you just use the SPL, yeah, now I'm not pretty sure how can I show the vertex 1 and the vertex 2 and also the width. So here, like this one, it doesn't show the vertex 1 and the vertex 2, it's only just showing the width like this one. I guess this one, right? I need to put the u comma v. I need to put u comma v. This is the case. So the original code does not have the u comma v. So if you call this one, I guess now it is working. So if I call again, and if I call this press, oh, I print this one. This is also print with the u comma v. I print the key here. Actually, the width can be shown without the key. No, this is not the flight shell. This is only the shortest path length. So let me just start from the first. It cannot get this code properly. I'm not sure. So if I copy, if I copy and paste the code here, and if I put the print width, it shows the width like this one. Okay, as you can see, there is the width u comma v, u comma v. It can be seen here. But if I use the original code here, if I use this width comma u comma v, it doesn't show it. Okay, you can just use the code here. Okay. I copy and paste this one in this part. So just use the shortest path length to show all the information. So this is the width between the DFW SFO. This is the shortest path length. So if you check on the Dijkstra algorithm, every time we do the repetition or the iteration, we will check the possible dz and du. So this is the dz and du for every of the iteration. Okay, this is the code and book, and then the author also use the Floyd-Warshall. They also share the Floyd-Warshall algorithm, and this is the code that you already saw on the PowerPoint. And let's say we are going to use the figure 1414 for this case. Okay. So we want to check the original vertex count and the original edge count. And after we are doing with the Floyd-Warshall, we can create a closure, which is a new graph. We call this is the graph star. And then we can see how many edge count are added into the graph star. So the original edges are 13, and when we find the connectivity or we find the reachability between all the vertex, we can have the total 21 edges. So in the transitive closures, there are 21 edges, including the 13 edges which are the adjacent with additional edges, which is directed edges. Okay. I give another code which is shortest path from external resources. This is maybe I saw some of you who are doing the presentation for the progress of the team project. You are using the additional library or you're using code from other resources. Yeah, I'm okay with that one. Of course, you need to check whether the code really works with your data and it is verifiable with the original Textra or not, or it is really the same with the uh, original shortest path algorithm or not. So for example, yeah, you can use the network X. The network X, it is the graph. The last time I think I mentioned to you with the network X, this is a graph library, and you can create your own graph. Let's say here I'm using NX to shorten the network X. And then the G is an object that I want to create. Let's say I'm going to add one node A. And then I'm going to add node from B to C. Sorry, I add nodes and then I have two nodes. This is B and C. So that means I have three nodes, which is A and B and C, but there is no information about the edge. Let's say I have this one. I have another G, and then I have node A, and then I have node B, and then I have node C. Now I have an edge from D to E. Okay. So this is the edge, and then I have another edge from A to B. And then I have another edge which is 1 and 2. So you can see I'm adding a node which is A, B, and C. I add node A and B and C. So I'm adding edge 1 and 2. Because there is no node 1 and 2, it automatically gives the additional node, which is 1 and 2. And then I'm adding edge. What is the edge start? So this is like a pointer. Okay? So Python is based on C. I'm adding edge. It is a tuple. So I'm going to add the edge with the star edge. It means the pointer from this particular data. I'm going to put it into the graph. So there will be a new edge, which is D and E. Because D and E is not available in the nodes, it automatically added into the nodes. And I'm going to add another edge, A and B, and I'm adding the edge, star edge into this graph G. So the A and B will be added. We can see there are 1, 2, 3. There are 3 edges. So A, B, 1, 2, and D, E. And those are the nodes that we have in the graph. So this is the way to create your networks. So I saw some of you already have the networks. And if you are going to make a bigger data, let's say now you have only 10 data. If you are going to make 1000 data, you can use this way and then you can increase into 1000 node. And if you already have 1000 node, maybe you want to increase to 10,000 node. Or if you want to increase to 100,000 node, then you can make random. Let's say the random number between 1 until 1000. So you can do repetition. And after you have those data, you can run with your algorithm and you can show how many times that you need to run with the 1000 data. how many times that you need with 10,000 data, and how many times that you need to run the 100,000 data. I took a code from this link. Okay? This is the Dijkstra algorithm. So in this code, you can check, okay, because some code they have the very small information. You cannot figure out whether they are really giving you a result or not. So let's say this is a graph, and it's very simple to make the graph. They just use a list. So list here means array, and in the authors of the book, they create graph and they're using object, so it's different. If you are using list, it seems simple. If you want to use this one, that's also fine. Let's say I'm going to make a graph, okay? And the graph is, yeah, this is the original example actually. So we can have the edges x comma a, and the width is 7. X comma b, the width is 2, and I want to put all of them into the list. So the idea is the same. Okay? With the previous example in the outer, we want, let's say I have the information about the airport mileage, SFO to LAX 337, like what we saw on the book example. And I'm going to add this one into the graph. So the graph dot add edge will be the star edge, which is this is the list, and I'm going to add each of this element into the graph. So I can check only one edge, because this is the last one, so I can see this is the last edge that will be printed here. And yeah, you can find other resources about the Dijkstra algorithm. In this case, yeah, I use this one. This is from the link that I shared above. So when you use other resources, please mention what is the link. So here I use a link. So please share also the link that you use if you use other resources for your Dijkstra. The idea is the same with the book's author. However, they try to use a list, and then yeah, they make another way, not using the priority queue. They use only the, like this one. If you see, this is the relaxation node. Okay. So if you want to run, and then you can see, let's say I want to see the distance between the PWI and SFO. Then the graph, which I refer to the book authors, it can show the shortest path is from PWI, and then it goes to ORT, and then finally can go to SFO. This is another code. So I took this one from another website. They make the graph like this one. So there are many versions how to create the graph. In this case, now they are making with the matrix. If you still remember, we have the adjacency matrix. in the graph. We have this graph with edge list structure. Okay, we have, if you see this one, this information is using the matrix information. It depends on how you can define your data. If your data is about the matrix, then you can use this code. Okay. So this graph will have the constructor, and then it will show the solution once you find the solution. And this is the minimum distance or the shortest path with the tree. Okay. And this is the Dijkstra algorithm. So the idea is only with the edge relaxation, they have this code to manage the edge relaxation. This is the original data. Okay, this is the original data from the website, but I would like to change it to the graph that has been shared by the book author. So this is the mileage from the airport mileage. We can make this kind of matrix. This matrix means from one node, this is 0, 0, 0. So it means this is the distance from its own airport. And we have 337 from airport 1 to airport 2. And this is the distance from airport 2 to airport 1. So you can see that is like symmetric. This is symmetric. The distance are symmetric. When you create this kind of matrix, the computational time will be higher. Okay? So if you check on the graph section in the first part, you will see that the matrix is n power of 2. N power of 2 for this kind of matrix. You can use this one, and of course you need to check the big O notation. Okay. Even though you are using the Dijkstra algorithm, okay, maybe the team 1 use Dijkstra algorithm, but the team 2 use Dijkstra algorithm 2 with different structure, then the big O will be different. Okay. If the team 1 use the Dijkstra algorithm with edge list structure, then maybe the worst case will be, I don't know, n log n. Yeah, it depends. Or maybe, yeah, if we need to see the code. That's why I want to see how you can analyze your algorithm. In this case, I can see that this is O(n) power of 2. If we use the edge list structure, yeah, this will be lower than n power of 2. Yeah, I give several examples from other websites. You can check by yourself which one is the best for you. So this is another example with the matrix, okay? And it shows every distance. So you can see what are the codes that is good for you and what you want to show on the result. So that's why when I look into your video, some of the teams are not clear about the output. In this case, the output is to show the distance from the source. So this is the distance from the source. And you can see all the details from the source, which is from 0 until 8. And then we can see this is the shortest path. from 0 to 3 and then 8. This is from 0, 3 up 2 and then goes to 7. Okay. Okay, that's about the shortest path. If you are doing with other kind of problems, if you are not using the shortest path, also please consider the same thing that I mentioned this one. Whenever you took the code from the other link, please mention the link. Okay. And then yeah, please check what will be the output from your code. Okay, any questions? If no question, then I will continue with the next section. So the next section is about the binary search tree. I guess you already know the idea of the binary search tree, but we are going to know more the details about this binary search tree. The binary search tree, what is the definition? And then there will be some kind of mechanism that we are going to check, which is about the insertion and deletion and what is the performance. The binary search tree. In the binary search tree, the keys are assumed to come from a total order. You still remember total order? It is based on the mathematical equation. Yeah, we have the total order relation, partial order relation. Okay. So we learn also about the total order in the tree section. Order maps. If you still remember, when we learn about maps, the key is not in the order, but we will use this one, order maps, to understand about the binary search tree. So the keys are assumed to come from a total order. This is the assumption. And the items are stored in order by their keys. This allows us to support nearest neighbor queries. So items with largest key less than or equal to k, or the item with the smallest key greater than or equal to k. So that's what we call as the nearest neighbor. If you find out the binary search, okay, in the previous, I think it was before the mid exam. Okay, we learn about the binary search. Okay. In the binary search, we can perform the nearest neighbor queries on an order map that is implemented in an array sorted by the key. So if I have this is a sorted, this is a sorted data, and then I want to find 7. How we can find 7? We have the low, middle, and high. And then we want to check 7. Where is 7? Whether 7 is the same with the middle, or 7 is less than the middle, or 7 is higher than the middle. 7 is less than the middle, then we go only to the left. And then we check the L and the new M and the new height. Again, we will check 7. 7 equals to the mid or the lower than mid or higher than the mid? You know, it is higher. So we have the new L, the new M, and the H is the same. And then we will check whether the number is equal to the M or less than M or higher than M. And at the end, we have the L equals to M equals to H, and then this is what we search. If you are doing with the linear search, you will search one by one. Okay. If you are doing the search one by one, it means it will take ON. Because we are doing with this binary search, it will terminate in the O log N. The log N is mean like we can cut into the half. So the search table, okay, if you are still remembering about the map, we have the table, which is similar to the concept of the map. In search table is an ordered map implemented by means a sorted sequence. So we store the items in array-based sequence sorted by the key, and we use an external comparator for keys. If we are searching, so it will take O log N. It use the binary search. If we are inserting a new item, it takes ON time. In the worst case, we have to shift N divided by 2 items to make room for the new item. So if we have a new item, okay, insertion will take N. If we want to remove, it will also take N times. In the worst case, we have to shift N divided by 2 items to compact the items after the removal. So the idea is almost the same with the array, okay, because it is in the array-based sequence, and then the key has been sorted. The lookup table is effective only for order maps of small size. Okay, so this is the key point: order maps with the small size, or for maps on which search are the most common operations. So with the order map, if you are doing a lot with the search function, then it is good. Because if you are doing with the insertion and removal, yeah, it takes ON. If you are doing search, it takes log N. Okay. Usually like the credit card authorization, searching what is the key of the credit card. Okay. So it will use the search tables. So sorted map operations, you know, in the sorted maps, it is similar with the dictionary. So we need to call the key. This is the standard map methods. If we call the key, then we know what is the value. And then if I want to check mk equals to phi, then it will replace the existing value if the map already contains an item with key equals to k. So it will update the phi with the newest one. And if you delete, of course, you are going to delete the key from the sorted map. The sorted map ADT includes additional functionality, and it guarantees that an iteration reports key in sorted order. and support additional search like find GTK. GT means greater than. I want to find the key which is greater than K, or I want to find range. So I have the starting and stop. So it comes to the new kind of concept. We call it the binary search tree. I think due to the time limitation, I will continue this next week.